Peter, welcome.
Thank you.
Welcome everyone to Climate Chat. I'm your host, Dan Miller. And today we have a very special session where we're speaking to Peter Ditlevsen from the University of Copenhagen, who wrote a very interesting paper that we've actually covered a lot here on Climate Chat previously on the AMOC and when it may collapse. And so, Peter, first of all, welcome. Great to have you here. And I'd like to start by just asking you to give us a little bit of your background, where and what you studied and how you sort of came to this path of talking about the AMOC.
Yeah. So for me, my career has been sort of the long and winding road. So I started out. I'm a physicist and a professor of physics, of climate physics now. But I started out in atomic physics, did my PhD there, and had a postdoc in Berkeley early on. And from there, I had to go back to Denmark. Denmark is a small place, and my wife at that time had a job at home. So when we went home, there were no jobs in academia. So I got a job at the Danish Met Office, and this was the first time I had anything to do with the geosciences. So this was meteorology. So I taught myself meteorology and made my way back to the university, teaching meteorology, and got into the group of people doing ice core drilling in Greenland and Antarctica, and that sort of got me started in more climate-related research, looking at past climates and especially the very rapid climate change that we've seen in the paleoclimate record from Greenland. These are the Danskar Ødsker events that were completely unknown to anybody before they were discovered in the Greenland ice. And for many years, it wasn't really known what these events were. But nowadays, we believe that these were actually turning on and turning off of the AMOC very rapidly, from climate change of 10 degrees within a decade, which is something completely unseen in comparison to what we see today of 1.5 degrees in a century. So this was what got me started on these thoughts about what can really be going on, because this is what we call a nonlinear phenomenon. And my background is in theoretical physics, and I've been also studying turbulence and chaos and really non-linear aspects of the system. And of course, as you all know, weather is very chaotic, and the whole dynamics of the atmosphere cannot be understood if you don't understand chaos. And then a couple of years ago, I had the luck of with very good colleagues around Europe, getting funding for a big European center that I've been leading on tipping points in the climate. And tipping points are, tipping points is sort of a hot topic today. And when we started this, the first thing we sat down, and we sat down in Paris, and this was unfortunately just prior to the pandemic. So a lot of the project has been actually on Zoom, because short after we started the project in Paris, we were all grounded in the pandemic. But anyway, the first thing we started discussing there was how do we understand tipping points? What is a tipping point? And of course, half of us has this very mathematical background, saying, "Wow, this is a bifurcation in a dynamical system sense. This has very specific meaning, what that is." And other people from the more sort of observing side, like geologists and so on, say, "Okay, we see these rapid changes. These are tipping points." So it was sort of a very vibrant environment to get to understand these things from different sides. And actually, it's in some sense we have a cultural clash, in the sense that we've been understanding it as physicists. I've been understanding tipping changes in things. You can imagine magnetization or phase transitions, ice becoming water, and all these things.
Mm-hmm.
And we have this complete theory built around it. And on the other side, you have geologists and geophysicists seeing these rapid changes, and somewhere in the middle ground, you have the climate models, which are sort of, let's take the big computer, try to put in all the equations that we know in a rudimentary fashion, first for the atmosphere, and this is taking 100 years, more or less, to actually precisely 100 years, because the first paper on this was by Richardson, 1924, which was a forecast, numerical forecast of, as I recall it, May 6th, 1910. It was a forecast for 6 hours. And so this was a hint cast, because he was an ambulance driver during World War I, and he spent the whole of World War I sitting doing that calculation, and it turned out to be a miserable forecast for 6 hours. And today we know he did it all right and all that, but it took up till the 70s before we could actually make a forecast that was better than that's a whole story. And so I can elaborate on that. I can also not do it.
But you came to do modeling of the AMOC, which
yes,
turned out to be a very controversial
then, that part
project.
Came later. Than the whole ocean part came later, and the AMOC is probably next to the El Nino in the Pacific, which goes east-west. The AMOC goes south-north.
Mm-hmm.
Is one of the largest variables in the global ocean. Of course, we have the circumpolar current in around Antarctica, but that's sort of stable. It just sits there and rotates due to Earth rotation. While the AMOC is a system, also like the El Nino, that's very non-linear. And already in the beginning of the 60s, actually 61, Henry Stommel, an oceanographer, made a sort of very simple two ocean box model of the AMOC, where you had sort of a channel in the top ocean, a channel in the bottom ocean, and driven by buoyancy, or the density difference between two waters, he could demonstrate that there was a possibility of two states. That's, of course, a very simple model. You say, well, it has nothing to do with the real ocean and so on. But that sort of started the whole mindset of nonlinearity in that ocean current.
Okay.
And then, of course, afterwards, the weather models, if you want to predict climate, you need the oceans. The oceans dominate everything. And in the beginning, when they did climate models with the atmosphere only, whatever you got out depended on what was the surface temperature of the ocean you put in there. So ocean is everything. So since then, ocean models have been very crucial. And this was also what was awarded the Manabe Nobel Prize for actually making the first ocean atmosphere model, but especially the ocean part of that of the model, and since then, oceanographers have demonstrated in these models that they do show the same two different states of the AMOC, that it exists in these models. And that's, of course, what made me wonder about it.
So actually, before
So,
you go, you're now getting to the part about the AMOC, but before we talk too much about that, can you tell us in layman's terms, what is the AMOC, and also how does it relate to the Gulf Stream, which I think is a little bit
yes.
better known?
Yes, which is a which is a very good question, and which I have been, also pondering with, because there was after I gave an interview to the Guardian in
Right.
Britain, they had a big discussion because they wrote that now the Gulf Stream is ending. Now, in some sense, it's a question of terms. But what is the tradition in the ocean is that we name things by the currents, the dominating currents there are. And it's all water, of course. And the water somewhere in the ocean doesn't really know what's driving it. It can be driven by buoyancy, I mean, heavy water sinking. It can be driven by the wind across the ocean that blows it off. And of course, both things happened at the same time. And the wind blowing, and that's the westerlies blowing from the Mexican Gulf along across the Atlantic, makes the Gulf Stream flow. But that's of course very narrow in the surface of the water, because when you get into a few hundred meters into the ocean, you cannot feel the wind. And the flow up across along the American East Coast and so on has to do with Earth rotation and what's called the Coriolis force and all that. So the Gulf Stream is really the top part, but you can also say it's the top part of the AMOC, which is also northward moving waters along the American coast, but much deeper layer that is driven by the sinking of heavy water, cold and salty waters, which is also sometimes called the Greenland pump, that pumps water down. And this is a huge body of water because it's much deeper, it's slower maybe than the Gulf Stream. So you can almost think of the Gulf Stream as a hot river meandering through the North Atlantic and then turning over towards Europe, while the AMOC is sort of the big water mass that slowly moves heat up. But of course, in the top of the ocean, it's the same water. It's just forced by two different forces. So, but I
By the way,
tend to
we should say, we haven't
it's
said it yet, that AMOC stands for Atlantic Meridional Overturning Circulation. So
Yes.
that's something that's probably worth saying,
Yes,
because
yeah, that's
using
true.
the
Yeah,
shorthand the
let me
whole
say
time
that
here.
again. So there are, of course, what we call eddies or gyres all around. But now, since the Atlantic is limited by Africa, Europe on one side, and the Americas on the other side, it's like a channel. So if you then look at what happens to the water all the way across the channel, so whatever sort of goes forth and back around that channel doesn't really count. But what happens is that in the top water, there's northward flow all across the basin, and it then sinks, and then there's a southward flow in below. And of course, these two things, they have to balance, because the water cannot run to the sides.
So it's like a
So in
conveyor
that
belt. It's
sense,
very often described as a conveyor belt.
yes. And the conveyor belt is a very nice picture of this, the water that's conveyed all the way up. This picture goes back to Wallace Brooker that put it up in the 70s. And he actually envisioned a sort of global conveyor belt, that deep water would really flow all the way around into the Indian Ocean to the Pacific and get up, come through the Indonesian archipelagos and come back and all that.
Okay.
That we really don't know.
So
To be
let's get
honest,
into now what your paper is all about. And
Yes.
there's a link, by the way, to the paper if you're watching this on YouTube. Eventually, when we post it, there's links to the paper down below in the comments, and also if you're listening on Clubhouse, there's a link in the comments there as well to the paper. But before we get into the shutdown part, can you just tell us what's happened to the AMOC recently in terms of slowdown? Like what do we know about how much it's slowed down in the past decades?
So that is actually a big discussion if it has slowed down. Now there are several problems. The AMOC, since it's so dispersed, and since we can only see the surface waters unless we go on a boat, sail out, and take a bottle or whatever down through the water column, pull up and get or even measure the flow at that depth and so on. We don't know. And since it's like what is it, 4,000 kilometers wide channel, it's very difficult to measure. But there is a campaign that's been going on for 20 years now, which has buoys sitting across. Of course, it's not a very dense net of buoys, and they then go down and up and measure the flow at different depths. So we do have a measure since 2004 of the AMOC, and there's not really a clear sign in that of a much of a decline yet of the AMOC. But then there's another much more indirect measure, which is what we've been looking at, and that is this very mysterious thing that happens in the North Atlantic, which is called the cold blob.
Cold blob, okay.
The warm, it has another phrase. Anyway, but there's a part, it's called the Subpolar Gar, south of Greenland, the North Atlantic, where the surface water is not heating up in the same speed as the whole global ocean is heating up, because we're in a warming world. Our globe is heating up, the oceans are heating up, the atmosphere is heating up, and that's a big problem. But there's this part of the Northern Atlantic Ocean that's not really heating up. So that's strange. And there was a paper by Caesar, Ramsdorff, and other oceanographers that figured out, let's turn to the models, the climate models, the ocean models, and see what could that be. And they came up with a specific area, the surface water temperature at this area, south Subpolar Gar area, south of Greenland, that correlates well with the AMOC of the model and with the AMOC as measured by this rapid array. So the big advantage of having this surface water as a fingerprint of the AMOC, that is that, but that we've been measuring for 150 years, because that's where we have all the ship routes going from Europe to the United States and forth and back. So there are many measurements, and we have measurements going back to the 1870s. So this is the big data series that we have been analyzing. So just before coming to what we actually done and what we're actually looking at, what you can see in that record of the temperature there was that it was declining, which means that the AMOC was about to shut down, but then suddenly it sort of came back again and went a little down. So it's not really clearly going down. It's changing, meandering up and down. And that is really the thing that we are analyzing. Because
That you are analyzing, or you're not
yes,
analyzing?
we are analyzing.
Okay.
So coming back to tipping points, which in this case is really what's called a bifurcation, that you come to a critical point after which this flow is no longer stable and it shuts down.
Mm-hmm.
How do I know now that I'm coming to that point? Well, that has to do with the fact that what keeps any state, in this case the AMOC, in its stable, what we could call the on-state here, is that whenever the flow changes, feedbacks, we call negative feedbacks, would kick it back into place. I mean, one of the analogies would be, your body temperature is very precisely, I guess since you're in America, I should say 100 degrees. For me, it's 37 degrees, but it's just a question of units. And if you go out and it's 110 out there, you keep your
You're
body.
dead.
Well, you keep your body temperature because you sweat. You go into a sauna, which is very hot, and you sweat, and the evaporation of the water from your body keeps you 100 degrees, right? That's a negative feedback.
Mm-hmm.
The warmer it gets, the more you sweat, the more you're cooled. If it gets colder, you actually start burning blood sugar and to keep to heat up your body. So we have a system of feedbacks that, the colder it gets, the more sugar you burn, the hotter it gets, the more you sweat. That is a feedback that keeps you on track. When you get ill, that resilience is less, and you get a fever or you get undercooled or so on. That means that those negative feedbacks get weaker. And when the negative feedbacks get weaker, you would sort of, by whatever kicks you in one direction or the other, make you change more slowly to one side or the other. It takes long. If you're kicked to one side, it takes you a longer time to get back. And this is exactly what happens when you approach a bifurcation or a tipping point, critical point,
Mm-hmm.
that as you get closer, the negative feedbacks get weaker and weaker and weaker. And at the point, they disappear and you drift off to the other stable state that would take you down there.
Mm-hmm.
So this is this fact that the system gets less stable. You see larger variations. Technically, we call it increasing variance.
Right.
That is an early warning signal of a transition.
So
That's
maybe
one
another way
way.
of saying it is, you're saying you were watching the temperature below Greenland. We see this blue blob, the cold blob, which doesn't make sense. And when you look at maps of global warming, you see everything is in red because everything is warming up except for this one spot below Greenland. And you're saying, okay, that's this signal. But now you're saying we didn't see it just going down, which maybe everyone would say, hey, if this is going to shut off, I expect it just to keep going down until it's off, like I don't know, other things we're used to, a light switch or something. But what you're saying is, no, we're seeing it kind of going up and down. And that's actually a signal that something is becoming unstable and ready to flip to a different state.
Yes, exactly.
So it's not good news that the cold blob is in a steady decline.
No.
Yeah. Okay.
So
That's very interesting.
that's very precisely how one can put it. So, and the other early warning signal is also that it starts to get slower. So if it's kicked off to one side, it takes longer time for it to come back. That means
Right.
that the correlation time for it's called the increased autocorrelation in technical terms, or critical slowdown, as I would say, as a physicist. And these two factors, they happen here. Now, when you're very close to a bifurcation point, this happens in a very specific way. Another analogy that I, as a physicist, would put up is a phase transition, which I was also talking about later. That ice melts into water, and solid iron melts into liquid iron. That happens to all materials. I mean, even if you take wood, put it into an oven without oxygen, it will become a liquid. The reason you don't see that is because it starts burning, which is a chemical reaction. But all materials have a melting point. Now, when you get very close to that melting point, all materials melt in the same way. That's called a first order or second order phase transition. It happens when you're close enough. It happens in a specific way, in a universal way. Now, the melting point, when it happened, what is the melting point of iron? What is the melting point of ice, and so on and so forth? That depends on the specifics. So now you can ask, when will the AMOC collapse? When is the melting point or the transition point for the AMOC? Well, then you go and ask the climate models, but they are all over the place. Not quite all over the place, but they do not agree on where it is, because where it is depends on the specifics. But how it happens doesn't depend on the specifics. And how it happens includes this increased variance and increased autocorrelation. So if you instead look at that, say, okay, now I'm here on the curve, which means that now I can actually, from here, extrapolate and tell, at that time I will be at the critical point. And this was what I did, and got this, to me, very surprising and scary result, that this is in 30 some years.
Right.
And I say, well, this, I cannot publish this. This is,
Really?
Can this really be true? So I called in a professor of statistics, who happens also to be my sister, to have a look at this with me. So there we pulled out the whole big machinery of statistics to see what are the probabilities of this and that. Because of course it's uncertain when is it going to happen, because it's these measures of increased variance and increased autocorrelation, these are statistical measures. So it is all in a chaotic situation. So we need to look at the statistics, and that much larger calculation actually confirmed what I have found in much simpler ways. So
now James, I interviewed James Hansen a few weeks ago, and I'm sure, as you know, he's also predicted that the AMOC would shut down much sooner than people said back in 2015 or 16. He did the ice melt paper. I can't remember what the year was. Sorry about that. But so have you ever spoken to him about this at all? And
no, I haven't. Maybe I should. Sure.
I'd happy to introduce you. But so he came up with the same thing, and he's, I understand, working on a paper to also talk more in depth about the AMOC. The cause that he described was fresh water coming from the melting Greenland ice sheet and the Arctic, and that fresh water staying sort of on top of the ocean because it's lighter, it's fresh water, not salty water. And that sort of puts a barrier on this overturning, and that's what's causing this to slow down. But I understand another part of it, and I'm not sure if I got this from him or just reading about it, is that the AMOC is also, the current itself is saltier than the other like brings its own salt to the party is a way of, is that correct? So when it slows down, there's also less salt water to run the conveyor belt.
Yeah.
Is that a correct way of thinking about it?
Yeah, it is. It is a correct way of thinking about it. One could actually, and that's that's sort of taking it to an extreme and say, this was sort of the old Stommel way of looking at it. You can imagine that the ocean works on itself, and the way that the water in the south gets salty is by evaporation of fresh water. So that fresh water ends up in the Northern Ocean, right? So in principle, you could have the situation where the southern water became so salty that it would start sinking, and that would take the conveyor the other way around.
Oh, okay.
So that would, but that is, we know from models that it's really not what is happening, because it would just weaken it, because the density differences would be smaller. But that's sort of a way of seeing this seesaw way of acting on it. So the saltiness comes from evaporation, and that fresh water is dump. But that's to return to James Hansen's idea, which I completely agree on, that the fresh water, it's a very strange thing that I'm saying, well, Europe is becoming Alaska. It's very scary and so on. In a warming world, how can global warming give a cooling? That's counterintuitive, and that comes from, of course, the more input of fresh water from melting of Greenland, more export out of the Arctic Ocean, more river runoff, maybe from areas that does not dry out, but also just more precipitation into the ocean. I mean, it's something that we rarely think about, but in the mid-ocean, it rains as much as here. It's just never measured. So that's also part of it. But that also means that, I mean, if you know the east coast of Greenland, it's very hard to get there. It's very hard to do measurements. So all these four factors, Greenland, Arctic Ocean, river runoff, and direct precipitations, they're very poorly constrained. So we don't know how much fresh water is coming out. We know, also, as Jim Hansen says, well, it's coming in there, and more is coming in there, and that is something that could stop the AMOC.
Actually, so what I'm hearing actually is very interesting, because I think Jim Hansen's looking at it from the point of the physical flow model, and what he's saying is that the IPCC has the ocean mixing wrong, that they're assuming the fresh water gets mixed in below much more easily than it really does. And so when it doesn't mix in, it stays on top, and then it physically shuts down this thing, the AMOC, which is where he's coming about it. But what I'm hearing is that you're coming about it from a totally different point of view. You're just looking at the signal of the AMOC, not looking at the physical mechanism of the freshening. You're just saying, hey, I'm looking at this and I see an unstable pattern, which means it's coming to a bifurcation, or a transition from the on state to the off state. So you're looking at it really as complementary. It's not like you're not studying the same exact thing. You're coming to the same conclusion using two different methods. Is that right?
Yeah. And that's, of course, also what sort of scared me when we published this, was that I'm at odds with the IPCC.
Right.
And I mean, there's somebody you do not want to be at odds with, it's the IPCC, because that's a lot of research going in there. And in my view, the problem is that the climate models, first of all, they're all over the place, even in the latest generation. But none of the latest generation are these called semi-6 models that I can return to in a moment. They do not show a shut off in the 21st century. Some of them show maybe a shut off much later, but in my view, this is pretty much in line with all other predictions by the climate models. We've seen Arctic sea ice disappearing much faster than the models predicted. We see extremes and droughts and so on in the real world now as we speak than the models predict. And that's because the models are pretty conservative. And in some sense, you could say, and somebody might, I hope not be offended, but might disagree with me, that since they are a large part of the physics of the climate models are what we call parameterized. They're not really based on physical laws, because you cannot really do that in a 100 by 100 square kilometer with one temperature. You cannot really describe the clouds in there. So if you want to describe the clouds and their radiation and so on, you have to make what's called a parameterization. You have to make a modeling of that is based on observation. So that's an empirical part, and that's nicely done. And what data can you put in? Well, you can only put in past data, which is the past 100 years, the 20th century. And the 20th century climate has seen a very sort of one-to-one linear temperature increase with CO2. So we're in the linear regime. We're far away from the tipping point or anything. But when we get to that, in some sense, in order to have the stability of the models, they are too linear.
Okay. Well, let's get to
another way
of
quickly describing
this is Eli. Go ahead, Eli.
That yes, the models are validated on empirical data, but the data set doesn't capture all of the dynamics that we should care about.
Yes. Yes.
So let's get to the crux of your paper, and maybe you can just tell us. So the AMOC, the Atlantic Meridional Overturning Circulation, we just heard about how you examined it, looking at the statistics, etc. But you made a prediction about it shutting down. So could you just tell us what is the conclusion of your paper about the shutdown of the AMOC?
Well, the conclusion is, and of course, there are uncertainties and caveats and all that, and that should of course be said. But setting up the premise, taking that we do have a tipping point out there. With more freshwater forcing it, there's a tipping point out there. All models agree on that. They do not agree on when it is. Then, when we approach that tipping point, it happens specifically in a way along a curve with fluctuations like that. Okay? And when I take this fingerprint, and that's sort of the other big if. I mean, the big if in this, if being right, if is that it is a bifurcation and it does like this. The other if is the data that I'm looking at, which is the fingerprint, is that a true record of the AMOC? So taking that if and taking that if, then the conclusion is, well, we can see that we are perfectly on that curve, and we know that when we are at that curve, this is when we hit the transition point, the critical point, the tipping point.
And that's going to be your paper, I understand, said from 2025, which is next year, to 2095, with a midpoint around mid-century. Is that right?
Yeah. So when it hits is 2057, and that's of course, too precise a number. And then with the much more advanced models, we could set in these error bars, say, which in technical terms, confidence levels around that point.
Mm-hmm.
And the 95% confidence level is, of course, very wide. And since my co-author and sister, she was sort of the proud mathematician, she wanted the error bars and all that in there. And I said, well, this is it's a hard one to get out with, because 2025, that's in a very short time. But I mean, from the mathematical point, it could happen, and then we would be on it, right? That also means that we could actually be on it now.
Correct.
I mean, this is not something that happens tomorrow. It's something that happens over. My estimate would be 30 years.
How many years?
Shutdown, around 30.
Yeah, I was going to, that was one of my upcoming questions. Is like,
okay,
when we say it shuts
wait with
down,
that,
what does that even mean? Like, how would
Yes.
we see it? What time frame for the shutdown?
Okay.
That kind of thing. So go
Yes.
into that a little bit.
Yes, let's do that. So, what would I base it on? How long it takes? Well, again, I can go to the models. They're conservative. They do this and that. And there's just been a model. This is a sort of an almost last generation model where they have this shutdown, put in fresh water on the top, and it shuts down. And it takes around a century going from the on state to the off state. That is slow. I mean, a century, that's where we start not to care, right? For 30 years, we care. Now, if I go somewhere completely different, namely on what happened in the past, and look at the ice core data, well, there, the shutdown happened in something like a decade. So somewhere between a century and a decade. And my sort of intuition on that is, this is something that happens of the order 30 years. And I think also, since we say this happens, 30 years out in time, so we are at these things, and I think part of why our paper got such a huge attention, which I think is good, because we need to do something about climate change, is that, well, people have been saying, and probably, I mean, unfortunately, people have not been listening as much to Jim Hansen as they should. But that's a different thing.
I think that's a general true statement, I think. Yes.
Yeah. A lot of the predictions have been, well, Greenland might collapse, Antarctica might collapse, and so on. And this happens in 100 years, 200 years, or 300 years. And I sort of speculated after this. I know my grandparents. My great-grandparents, I don't even know their names. These are people I don't know, right? I'll care about my grandkids, and maybe if I get old, their kids, but then it's not my family anymore. And I think this is something that makes, on a human scale, 30 years very different from 100 years. Mm-hmm. And I think this could be the necessary wake-up call for us, that it's not just a question of changing, but it's a question of the speed in which we change things.
So but we have two different 30-year things happening. One is your center point for the collapse is about 30 years from now. And that, let's be clear, that's the beginning of the collapse? Is that?
Yes. Yes, that is the beginning of the collapse.
Beginning of the collapse, which could be 2025, and it might actually be collapsing in 2025, and we maybe would still have trouble even figuring that out. But once it starts, then you're saying it takes about 30 years to go from this on state to the off state. Would it be fair to say that Northern Europe will go from its current climate to a very cold climate over a period of 30 years once the AMOC begins to collapse? Is that
is also what models say? I mean, there have been mod. There was a mod that was run to the collapse and showing that agriculture in Great Britain would be like what you could
Decimated.
do in northern Norway, and so I mean it's
Yeah,
it's
I read that paper about the UK. It was one of the few papers where they looked at a particular country and said, "What if the AMOC collapsed?" And
yes.
they said it loses UK loses like 70% of its arable land or something. We also had Matt England on, who wrote the paper about what happens during after an AMOC collapse, not when does it happen. And he also pointed out there in his graphs that the amount of rainfall over the entire Northern Hemisphere drops dramatically and with an AMOC collapse, because that warm, moist water going up is no longer doing that, and that affects agriculture around the entire world. So maybe we'll talk about the impacts a little bit more, but this is really interesting. First time I'm actually hearing about the time frame for the collapse. So 2050s plus or minus a few decades, and about 30 years to go from on to off.
Yeah. Then with that in mind, I would like to put in a little bit of optimism. Two things for that. One thing is that since this is just an extrapolation, it must mean that this can only be business as usual, right?
Mm-hmm.
So as we have gone here, and we have a business as usual, and we can, of course, hope for some actions that would slow things down. And that is unfortunately not being seen now. I mean, if you look at the CO2 record, the Keeling curve from Hawaii,
That does not
but
look good.
it's not actually. It's so scary that it's not even exponential. It's super exponential.
Positively correlated with COP meetings.
With what?
Yeah, with the COP, if you look at all the COP meetings, every COP meeting, it just keeps going up, and you can blame it on the COP meetings because they correlate over time. But
but one thing that is
yeah.
one thing that one could put as a positive thing is that actually the carbon footprint per capita is going down. That was new to me. I heard it a couple of weeks ago, and I hope it's true. But that is, of course, we're getting more people.
But the climate doesn't know how many
that's a
people we have. It
problem.
only knows what the total is. And that's
Exactly.
not going to. But speaking of things that might change, and this is a question I really wanted to ask you here. So one thing Jim Hansen did in our interview, and of course in his paper, his recent Global Warming in the Pipeline paper, he called for purposeful intervention in the Earth energy imbalance to reduce that, to basically, as he puts it, to reduce the geoengineering we're doing to the planet right now. We need to take purposeful action, which he doesn't get into the details, but he means what I call sunlight reflection methods or solar radiation management to cool the Earth. If we did that and focused it especially on the poles, we could reduce the melting in Greenland and the Arctic pretty quickly, actually, because we would basically refreeze them if we did it aggressively. Is that to prevent the AMOC from tipping over? Whether you like solar radiation management or not, I mean, it's just a question. Do you think it would actually have an impact on the AMOC?
So one unknown that comes in here is the sea ice, because then you would want to have sea ice around Greenland and so on, and the sea ice prevents the sinking the Greenland pond, so moves it south, and this is what happened back in the ice age, where you had this flickering of the AMOC. I mean, it's there are now some theories that what happened, how could it sort of start and stop then? Well, then you had openings on the ice, which is called polynya, where you'd have a lot of heat going into the atmosphere, and you would have sort of all kind of things happening there. I myself, I mean, my inclination, but this is, I mean, in some sense, not a scientific statement, but more on a personal level. I think we should be very careful about deliberate geoengineering. I know that we're doing geoengineering, but that's not deliberate, right? I mean, rice farming
how about personally now speaking personally, I think that the side effects, the negative side effects of purposeful geoengineering would be less than the side effects of accidental geoengineering that we're doing. In other words, the whole idea is to offset what we're doing, is to not let it warm so much and cross tipping points. One of the most important, I call the AMOC collapse the mother of all tipping points, because the impacts are not, I mean, yes, everyone talks about Europe getting cold, but that's like the least of it, really. I mean, it lower rainfall across the Northern Hemisphere. Jim Hansen thinks this leads to 10 feet of sea level rise this century, because that warm water going to Europe ends up staying around Antarctica, accelerating melting. So there's a lot of bad things that happen. But putting aside the debate on geoengineering, which is we talk about all the time on Climate Chat, and you are welcome back anytime to join in on that discussion. But still, the idea that the AMOC collapse is being forced by this freshwater intrusion from Greenland and Arctic, and that is that's the mechanism I understand, and that's the only thing I've heard so far. But we can offset that if we do it carefully. We can just stop the loss of ice, as opposed to building up a huge ice shelf in the North Atlantic, assuming we just do it correctly. Do you think that stopping that freshwater inflow or reducing it significantly is a way to preserve the AMOC, or is it once you kick this thing in, it doesn't matter anymore what you do with the fresh water? I'm not really sure.
No, but I think it is. I mean, since it is the fresh water that does it. I'm just skeptical in terms of the scale in which we had to intervene for doing that, which in my view would be tremendous. I
well,
mean,
we've had other people on
a lot of the heat in the polar regions and the global polar amplification of global warming, which means that the polar areas are heating about 4 times as much as the global. That's from the fact that we have heat transported,
right.
via the AMOC, but also via the atmosphere and so on.
It's also
and
ice
you don't
melt.
stop that by putting in mirrors in the Arctic atmosphere. Anyway, the radiation hitting the Earth is much stronger in the tropics than it is in the Arctic. And we are talking a lot about the ice albedo, which is cooling, right? But in the Arctic winter, it doesn't really matter because it's dark. So there's no ice albedo in winter. In the Arctic
not in winter, but in the summer there's a lot of ice melts, right?
In the summer there's a lot of ice melt, yeah, that is true, and of course the sun is shining day round in the Arctic. So
well, on this, let's see, on the sort of the same subject of I understand that an AMOC collapse, once it is underway, this is irreversible for at least centuries. Is that a correct statement? Or if it maybe we got this 30-year mark, we start to see it collapse?
Exactly. Yeah. That's a very good. That was actually my sort of optimistic note, that you can cross the threshold. I mean, this is the Roadrunner thing again. You're over the cliff and you can run back if you're quick enough. that means that even if we say we are, across next year, we will still have this of the order, but probably not full 30 years, because then we would be below. But as long as we haven't moved too much away, there's a possibility of coming back.
But coming back in that particular case, I mean, if we cut our emissions to zero by the reducing cumulative emissions by 2% a year at that point, because we're talking about 2.4 trillion tons versus 50 billion tons, something like that. But those things take decades to even see an impact. So that, to me, the only thing I can even think of, and you've thought about this more than I have, is sunlight reflection methods of some kind to stop that freshwater flow. Is there any, first of all, again, back to the question, will reducing freshwater flow, is that the kind of thing that should save the AMOC, or are there other things we can consider doing that would help save it?
That is a good question. I mean, the major source of fresh water in the North Atlantic is from melting the Greenland ice sheet.
Mm-hmm.
And there's just no way. I mean, there's a way you can paint it a color, right? But the color you want to paint it is white.
And
it's already white, right? So there's not much you can do to that, right? The only thing we really can do is reducing our emissions, because that's an immediate action on the radiative balance in and out. And of course, you say putting in mirrors and so on. What I would be very afraid of in geoengineering, especially mirrors and things, whatever you would put in the stratosphere and so on, is it is a hard commitment on several generations, right?
Well,
So
I mean, we had Doug McMartin on, who's a professor at Cornell who studies solar reflection methods, and basically we're doing it today, of course, on a massive scale. And Jim Hansen's Global Warming of the Pipeline paper points out that we are reducing shipping emissions, which is greatly accelerating warming far more than the models show. But as Doug points out, and I'm going to pick these numbers, I think they're roughly right, but not exact. We put up 100 million tons of sulfur in the lower atmosphere, and that's reflecting the sun and also creating clouds, by the way, very importantly, seeding and making them brighter and making them last longer. And then we're cutting that back because it's pollution that's killing millions of people every year. But in the lower atmosphere, that only lasts for about a week. But if you put it in the stratosphere, it lasts for about a year, but you don't get the cloud benefit. So he said you can reduce it by 95%, the amount of pollution we're putting up there, but just put it in the correct place, and you'll end up with more cooling. So I would say he's optimistic that the benefits of doing it outweigh the negative thing. And of course, if you stop doing it, in a couple of years later, you'll be back to where you were. Or maybe 3 years or something like that. So
if you look at the climate models, simulating through the period where especially Mount Pinatubo was one of the largest volcanic explosions that put in sulfur into the stratosphere.
Mm-hmm.
Then you see that all the models gives really a cooling blob and so on, much larger than you actually observed. So I think
again, it was say that again.
It's much larger than we then actually observed the global climate. If you look at the climate, if you just look at the global temperature records, it's a very tiny blip. Pinatubo,
half a degree or so, which is not bad for one volcano.
But in a very short time.
For a year or so.
So I mean, you would need.
No, you have to keep doing it. I'm just saying, if you decided to stop doing it, you said you're committing to it. you are committing to it that if you don't reduce your emissions, it's really dumb.
Yeah. No, but
Right? I agree with that.
I agree, but I think it's in some sense it's and I think from Jim Hansen it's a good rhetoric phrasing that, oh, we are already doing geoengineering, but we are not. I mean, agriculture, cutting down all the trees to put making soybeans for our cows and all the burgers, that's geoengineering.
Yeah.
But the purpose is not geoengineering. The purpose is to get Americans obese. And that's a completely different thing, right? And so we do a lot of things to the planet for other reasons.
Correct.
And I think the conscious thing we can do to climate is to prevent our pollution, to prevent our change of the climate.
Absolutely, totally agree, by the way. I mean, and I would say, and I think Jim Hansen also agrees, three things we have to do. One is to reduce our emissions as fast as possible. And secondly is to remove our past emissions because it's already too high. And that's expensive right now. And he thinks maybe we got to wait for that because the cost per ton is quite high right now. And then the third thing, which is not expensive, is actually to reduce the Earth energy imbalance purposefully in the near term. He actually, I think I'm safe in saying that he said we have to do that or begin doing that this decade to really prevent serious tipping points, including AMOC's only one of those, right? But let's speak about, get back to the AMOC in your paper. Go ahead, please, if you want to.
Yeah, I mean, you're right. There are multi-decadal commitments or multi-generational commitments, no matter what we do. And I think choosing which ones are associated with the least disruption and unpleasantness is something to weigh against uncertainties. Certainly, there are uncertainties associated with just about anything we'll do, but either we have to do something to address what we've done to the climate, or we have to do something about how civilization is supported by the climate and ecology that's being disrupted. So there's no avoiding multi-generational massive commitments. But in terms of sunlight reflection methods, I'll point out that it's not a strict on-off that all happens all at once, where I think that we are likely to experiment with spatiotemporally bounded sunlight reflection, for instance, to preserve coral reefs, because those ecosystems are both highly sensitive and pivotal to the rest of ocean ecology for the most part. And I think we will learn a lot along the way, and it's important also to accompany that by more theoretical and modeling work of the kind, actually, that your paper is, specifically what to look for and how to understand what we're doing and how we can empirically validate it and better predict the most optimal ways to do it. And what occurred to me as you were talking just now about that is it would be, lots of people are afraid that if we start playing around with stratospheric aerosol injection, which is not my favorite modality of sunlight reflection methods, it may be necessary in the short term to avert catastrophes, or hopefully not, but it shouldn't be off the table, at least not yet, I don't think. But it occurred to me that it would be really interesting to do an analysis kind of like the one that you did regarding, what kinds of what would it take to tip things out of balance by stratospheric aerosol injection. This is kind of counter to the butterfly effect notion that we'll do something small and it's just going to have these sweeping effects on everything, which I think is a misunderstanding of chaos theory. And I was wondering if you had any thoughts on that.
Mm-hmm.
I was saying doing your study, your type of study, but instead of doing it for AMOC Collapse, do it for the forcing of sunlight reflection methods, and will that throw the Earth out of balance on its own versus getting it back in balance, which is the purpose of doing it? But any thoughts on whether that would be useful?
I think it's it's a very very relevant, interesting question, and you know, it's always, as a scientist, when you say it's an interesting question, it's when you don't have a good answer to it. Because it's a very difficult question. Of course, now you mentioned coral reefs, and temperature is a problem. I mean, carbonic acids is, as I understand it, also, or maybe even a larger problem. And that one is not solved by increased emissions and then reflections to reduce temperature. So
Yeah,
there's side effects.
nobody on climate chat is for not reducing emissions.
We all agree
most of
with
us
that's the number
are
one
for
thing to
carbon
do.
dioxide removal.
Yeah. Okay. Now the other part, which is really a good thing, couldn't we, you know, let's put you know, the butterflies in very smart places and have them flap the wings here and there, and then you know, why are we heating our houses now? It's darn cold in Copenhagen right now. So why don't we just get, you know, a warm wind from Turkey coming up here? Like, if I flap the wing of a butterfly in the right place, and this is really the problem. Obviously, the answer is it cannot be done, because that's the whole sort of essence of chaos, that it is not predictable. And so how can I make any predictions in a chaotic system? And that's, of course, only because there's some robust features that you can tag into and do. And one robust feature, I think, is the connection between the global temperature and the carbon dioxide concentration, right? This is the one big thing. And the problem, I think, in discussing geoengineering at all, is that reducing carbon dioxide, reducing the greenhouse emissions will cost us on our economy, on the global economy. And that's something that politicians have a very hard time in telling other people that they should do, because then they'll not be elected afterwards.
So we have Stacy here.
In some sense, I have this feeling, and maybe it's a little bit cynical, saying, okay, having this thread of an AMOC collapse sitting there might be the necessary wake-up call to actually put in the investments that are necessary for a quicker green transition.
I agree with
It
you, by
might
the way.
sound a little bit
I agree with you,
naive,
because it's much more specific than the world is warming. They don't know, well, it's warming.
Yeah, exactly. Yeah.
AMOC is a particular time, particular set of impacts. It's something visual you can kind of imagine, you know, a little bit. So I agree with you on that. We have Stacy here, one of our co-mods, who has a question for you.
Hi. Yeah. Well, there are two things. The one, you mentioned getting elected, and I can't imagine anything being, I don't know, more damning than you didn't do anything, you know, when you could have. And I guess that's why my fantastical idea of the Scarlet Sea or something that you and your offspring would have to wear forever, that there'd be a registry of who didn't do something or who profited or whatever, and that you'd have to pay for that later on down the line. But I did have a question earlier, very early on. You mentioned something about in the time of a decade, there was a 10-degree shift or something, that this is in the ice record, and I didn't catch when that was. And you were theorizing that might have been an AMOC collapse or flickering or something at another
Yes.
point in time. Could you explain that a little bit more?
Yes. So this has happened. This is during the Ice Age, and the climate was very, very different during the Ice Age. I mean, Northern America was covered by the Laurentide ice sheet.
This is 10,000 years ago.
This is more than 10,000 years ago.
More.
It's 20,000 years ago. Yeah.
20.
The
Okay.
last shutdown was 12,000 years ago, just before we entered our present Holocene climate. So back in the Ice Age, we had this flickering. And so what happened was that you would have a shift. And of course, it was not man-made at that time. These were just natural shifts. And then, say, a few hundred or a few thousand years would go, and then it would shift back. So it's been flickering between these two states of the AMOC naturally. So these were just random fluctuations, and of course, had there been, I mean, you could speculate that civilization only happened maybe 10,000 years ago, but we've been basically with the same brain size for 100,000 years. How could that be? And then one could say, well, because, you know, at that time, a flickering of climate in 10 degrees in you know, Europe would maybe destroy civilizations and so on. This is, of course, a sort of speculation that's not really substantiated, because you have to find the archaeological evidence for failed attempts in order to make a claim like that. But this is this far back. But when it happened, even in that different climate, it happened very, very quickly. So that's what I'm basing my
Okay, so the only thing that scares me about this, you know, I have always dismissed climate deniers, naysayers, whatever, as they'll say the climate has changed before. How do we know that we're doing it? Blah blah blah. As who even cares who's doing it? Whatever, it needs to stop. Like, we should, if we can control the things that are making bad stuff happen, why wouldn't these clever monkeys do something about it? But when I hear something like, because I, you know, I'm here in church every Sunday, and I view, as Dan mentioned earlier, the AMOC, that's kind of like people, like all the floods and fires and stuff. That was just an appetizer, you know. Wait until the AMOC shuts down. And so to hear that, okay, it shut down, it turned on, and nobody was doing it.
But there were reasons back then. I mean, you know.
Okay.
By the way, speaking of that last shutdown, I understand came from a freshwater lake that was held in by glacial ice that broke through and flooded the North Atlantic with fresh water quite dramatically and suddenly. Is that confirmed, or still, or at least still?
Well, I think it's still up there, but I think it's fair to say it just happened. But I think we have to realize that what we're talking about here is, I mean, these people are not wrong. Yeah, climate has changed always,
of course,
but it's a question of timescales. I mean, if we are entering another ice age in 10,000 years, we're probably not due to this. But if we were, who would care? These are just, when we had ice ages for millions of years. It's a question of the timescale of our lives. I mean, nobody would say, I mean, the dinosaurs, they were happy animals until a meteor hit. It just hit, and in questions of hours, they were all wiped out. But before then, they lived happily in a very warm climate. I mean, there were crocodiles in Greenland, which was still Nordic, and that's a cold-blooded animal. So we have had warm climates. So nothing is telling us that this is the best of all climates, but it's our climate. This is how we live. we cannot migrate across borders, and we cannot. I mean, there are a lot of things we cannot do where it would be very unpleasant that things change in a high speed. And this is our understanding that, well, we are doing it. I mean, the thing is, climate deniers or skeptics, they are deliberately speaking against better knowledge. And there's just no, it's a little bit like, making sense with Donald Trump or whatever. I mean, it's not worth discussing it.
Yeah,
all.
that's true. So let's move on to my other audience. I have some other questions. Stacy, unless you had another question you were lined up with.
No,
Okay.
that's good for now. Thank you.
Great. So Arian, I'll ask you to unmute. Let's see if there we go. Okay, and I'll let you turn on your video here. Welcome to the stage. If you want to turn on your video, go ahead.
Yes. Hello. Thank you so much for hosting this, and I really appreciate your research and Dan, you furthering our understanding of this and activism. I have a question, and I would prefer that we focus on solutions than climate deniers. I think that slows us down. But my question, which may be unpractical because I'm neither an engineer or scientist, would be, could it not be possible that we divert the fresh water coming off the glaciers in that way, use that water, and also prevent it from flooding the ocean? I know this is a lot of water, but it would seem to me that it could be an important solution if it were physically possible.
Yeah. I mean, that's a lot of water. I mean, I can say now, actually now in Denmark, we have big problems with flooding. We're a very flat country and we've had a lot of rain, and there's just nowhere to put it. So that would be very hard. There were also some ideas of, couldn't we sail out into the mid-ocean and pour salt in the water to unfresh
Right, that was the other
water
solution
that comes out. And I think that's also a pretty unrealistic thing. And just to, I mean, in terms of solutions, and I know maybe if then just stop me if it's it gets too political. I think we do have almost all the technology that is already available now to develop, to do a green transition to a zero emission society. So why don't we do it?
Mm-hmm.
Well, we don't do it from the classical market failure problem. I mean, we are happy about liberalism and capitalism and all these things, but it has some flaws in it. And one flaw is the tragedy of the commons, right? Whatever I pay to reduce my reductions, everybody benefits from, right?
Mm-hmm.
But if I only do it and nobody else does it, then they benefit more than I do, right? Because I pay the whole bill. And that's why the COP conferences are of no use. Unfortunately, right. I'm very sad to say. And I am also very sad to say that the UN is in some sense a lame duck, right? Because
Mm-hmm.
it is based on consensus. The only thing that's not based on consensus is the Security Council. The Security Council of the UN is actually a powerful organization. They can enforce on other countries. If the Security Council agreed that, well, everybody has to reduce this and that, compensating for developing countries or whatever, they are actually legally capable of enforcing that. And I think in some sense, the clue for that why you need the Security Council is that it then has to be a security issue, right? Now
it's the biggest security
why
issue,
is
but
climate not a security issue? Right? And that is, I think, that we have to realize we are at a point where it is a security risk, because the livelihood of about 3 billion people, it would be unpleasant for me if this becomes a cold place, but I will not die. But 3 billion people in the tropics, if temperature increases from 95 to 100, then or 105, that's their livelihood, and that is a security issue. And I think that has to be the way to go, that we have to enforce on each other that this has to happen. And that puts a completely different mechanism into the economy. And when you're forced to do this transition, you do it in a smart way, and you get your businesses to, compete against the Chinese and so on and so forth. And this can happen very much quicker than it does. And I think we cannot wait for the cops to do that. But that was my political
okay. Well,
statement.
by the way, we talk about that kind of thing all the time here. We're not just talking about only the science. We talk about politics, communications, various alternatives like carbon capture, sunlight reflection, different ways to reduce emissions. I do have to say, though, that the last time that CO2 was the current value, 420 parts per million, sea levels were 75 feet higher than they are now. So it's not like if we cut our emissions to zero, that the melting would stop. It would actually continue for centuries at least, or something.
Yeah.
So there is that. That is why I think we need maybe, and when Jim Hansen says we need active measures, he's a very conservative guy, and you should really listen when he says that, and which he's saying now, which means he's really worried. So, Arian, I think you have a follow-up question. Arian, you raised your hand again, so. Well, maybe not. So we're going to go, okay. We're going to go to Bartosz, and you can start your video if you want as well, or ask your question.
Hello?
Yeah, we can hear you. Great.
So first I would like to maybe add, because our expert today just said that the only body that does not need consensus in the UN is the Security Council, but it does require consensus between the 5 permanent members, doesn't it? So while I could see France and UK agreeing on some ambitious climate plan, for United States and China, that's a really big ask. And I don't see any scenario within the next decade or so that Russia supports anything even moderately ambitious. And So how would you respond to that?
Yeah.
And because I know it's a difference, like consensus between 200 countries and consensus between 5 countries, but still, like the veto power in Security Council makes it more or less also requiring a huge consensus.
Yeah, so the question is, like, with the Security Council, with Russia having veto power, they're not so much for cutting back on fossil fuels right now. And what are your thoughts on that?
No, of course. I mean, now this is, I completely agree in the analysis, and of course, right now we are in a sad situation with the war in Ukraine and the Russians being aggressors and their war economy being based on export of fossil fuels. So that's of course completely unrealistic now. However, we want to see loopholes, and now actually Africa is now proposing that they would have a seat in the council, and they will probably get it without the right of a veto. And somehow, of course, you would say that maybe the vetoing is too restricted, since this goes back to the victories of World War II. And the world is very different from then. But
okay.
I'm not an expert in geopolitics, but it was sort of the only loophole I could see as a realistic way to go.
Okay, thank you. And we're going to go back to Arian for a follow-up question. Thank you, Barta. Okay, Arian, you're muted. Let's see. Oh, I have to ask you to unmute again for some reason. Okay, here we go.
Thank you. Thank
There
you
you
for
go.
unmuting me. Just a comment on the militarism. It seems to me that the military in all these nations, but especially in the US, needs to be transformed into a civilian corps in which the climate emergency is the major war that we're fighting. We need to understand that. But to do that, first, we need to understand that the wars that are going on, much of it due to American corporate greed and the Pentagon's interests around the world. We don't have control over our Pentagon in this country, in the US, that we're actually trying to transform the military into something different. And to do that, we may have to put certain corporate heads in jail because they're basically destroying ecosystems, and they're threatening all life, including human life, with species extinction. And we have yet to have the will and the wherewithal to do such a thing. I think that needs to start to be discussed.
Okay, thank you. Well, I don't know if you need to respond to that. I mean, I actually want to move back to your paper and finish up with discussion of the science of your paper. And that is, you've gotten a bunch of criticism, of course, about as any paper would. And I looked through like a summary of that. And one thing I found that was really interesting is that some of the criticism was saying, well, the AMOC signal is fluctuating. It's not really just steadily going down. And I heard now from you today that's actually a sign that you're right, as opposed to a sign that you're wrong. But rather than going, and then other things were like the temperature signal is not a good one. You could have volcanoes and everything like that could disrupt that signal over time. There was a lot of things like that. And a lot of like, oh, there's other studies showing it's not going to collapse. But of all of this criticism, what criticism of your paper do you find most credible or that you take most seriously? And how do you respond to that?
And there are two things. One thing is, as you say, this fingerprint, and this we are presently working on. Actually, we thought sort of very quickly that now we have to sort of have follow-up papers and this and that. But basically, since we published this paper, I've been, speaking with people like you. So it's been very, very busy. But what we are on to now is to be more assured using more advanced methods to be sure that which of actually many different fingerprints that have been proposed will be the best one, and how do we extract the very best one, the most reliable one of them. The other thing is to understand if this very, in some sense, reductionistic way of seeing a tipping point is what is truly happening, which is figuring out more in detail, how do we agree, how do we disagree with the climate models. And we still know that the climate models are pretty uncertain, but they are in some sense the best we can do. So we want to sort of close that gap between these climate models and what we do. And it's not an easy thing to do, because as you probably all know, that the climate models that IPCC base their assessments on comes from these coupled model intercomparison projects. So I would say climate model intercomparison, but coupled, that comes from the atmosphere and the ocean, so it's a historical thing. And then you say, why have a model intercomparison project? I mean, you don't compare models in when Einstein came with general relativity, they were not like 10 models, and then you could compare which was, how, let's make an average, right? The model is either right or wrong. But this is really, in some sense, a picture of the state of the art in climate science, that even though these models are hugely complex and they're run on supercomputers, you spend the electricity of a smaller village running a climate simulation for IPCC, and 50 different groups do that, and they have this sort of, you've all seen this sort of spaghetti band of projections,
Results,
and then
yeah.
sort of put the line in between, in the middle of that. And what it really reflects is that we are highly uncertain. And the problem is, the more complex a model gets, it's a little bit like the better the graphics gets for a weather forecast, the more you believe it.
Right.
And this is really not, in some sense, it's not science. I know now I'm being very, almost polemic, but this is the state of the art. But this is really what we want to look into.
But wait,
One
so
point-
speaking of it, Eli, I want to follow up on this.
Yeah.
One of the things in studying Hansen's view of the AMOC and talking about that, he mentioned that the models that show less mixing of the fresh water, they do a better job of hindcasting. And when you take a look at models that reflect past temperatures correctly, they predict an AMOC collapse. And the ones that don't show that, because they assume much more freshwater mixing, that they don't show the AMOC collapse. But is that a correct summary of the model's simulations, that the ones that reflect past temperatures more correctly tend to show an AMOC collapse faster?
Yeah, I think so. I mean, Jim Hansen is more of an expert than I am in climate models, to just say that. But so I'm sort of in some sense looking at it from a side view. But my impression is, having followed this through the past 30 years, is that as you put on more pipes and flutes to the model, and you do that for every generation, there's sort of a CMIP generation 1, 2, 3, 4. Now we are up in the 7th round. And what you identify at each of these rounds is, there are biases, there are things where it doesn't fit with past climate and so on. And then we put on another factor. A nice example is, I think was sort of was that the second IPCC report or third? I don't remember, but one of them predict, well, in 10 years we will have a warming of this and that. And 5 years passed, and it was not as much global heating as was predicted. And so that was because the aerosols, as we discussed before, the smog and aerosols that actually has a cooling effect from pollution, wasn't in the models. So that was put in and was corrected back, and then now you got the what fit with observations. And that's of course all nice, and it turns out to be right. But as a skeptic, you would say, oh yeah, well, yeah, you can always fit the things. And this kind of fitting, putting more and more things in there, also makes it more and more, you have to balance uncertainties over here with uncertainties over here, and sometimes you get biases over here compensated by something over here. When you suddenly put in soil moisture and vegetation and so on, and all these things make the models more, in some sense, more linear, and maybe more unrealistic in predicting the nonlinearities like an AMOC collapse.
And just to repeat it again.
Not only that.
Go ahead, Eli.
Yeah, not only that, I think it makes the whole endeavor a bit more circular in the following way. There was one soil model that explicitly incorporated the nitrogen and phosphorus cycles, and that in fact was kind of an outlier comparing to other models that tried to account for soil uptake, including biological carbon uptake. And I mean, the thing is that what they do is they add something, important to the model that hasn't been addressed explicitly. And then they go back and they have to make it fit, either with the data set that everybody is working on, or try to agree more with the other models, right? And basically this is what is called overfitting.
Yeah. Yeah.
So I want to get back to I think a key question, which I want to make sure I have your answer on, if there is an answer, and that is getting back to if we do cool the Arctic and try to stop the freezing of try to refreeze Greenland and stop the freshwater inflow that way. And let's say we are successful and we don't overdo it too much. Do you think that could rationally stop the AMOC from collapsing? Is that a method to try to address it? I mean, we'll also, of course, reduce our emissions and do those other things. If we're going to do that, we're probably getting at least more serious about reducing our emissions. But do you think that is a tactical approach to preventing an AMOC collapse?
Well, I would say it's very complicated. It is very complicated.
A good research question.
We are out. You know what? In climate science, I've heard expressions like guesstimates. As a scientist, which is this of course a mixture of a guess and an estimate, and when you know nothing, you do expert elicitations, which means you call up 100 people and ask, what do you think? And then you have a statistics on that. And
well, I'm calling up one expert right now.
Huh?
I'm calling up one expert right now. You?
Yeah, of course. So maybe
what's your guesstimate?
I would say, I don't know. And I would be very impressed, and I would like to hear if somebody knows, if somebody could really show me a sort of reliable calculation that would tell you do this and that, and that and that will happen, and you won't get this and that side effect, and this is the size of the thing. I don't really think I've seen that.
Okay, well, that's interesting in its own right. Something so important, right? But but look, I want to get to the other one. So, I mean, to me, saying that the problem is freshwater inflow, and here's a method to stop freshwater inflow,
that makes
suggestive
sense.
It might work. But you're suggesting that we could lower our emissions and therefore lower warming in general, and that might stop it. But actually, is that more than a guesstimate? Because as I pointed out, Greenland's going to be melting for a long time. If we cut our emissions today, it's going to keep melting at least at the level it is today, if not more. So is there anything to back that up, or is that a guesstimate that cutting our emissions could prevent an AMOC collapse based on your studies?
I mean,
your statistical studies.
The thing is, the problem is it's so close, but in some sense, say that we're right, that this is something that will happen in the mid-century, right? Now, if we could start get away from business as usual, lowering it, we are changing the speed at which we
push the system,
approach the tipping point. Now, if I can just skew that curve maybe another 30 years, now we're talking about technology in 60 years rather than in 30 years, or even more, 100 years. And if I can keep doing that for a period in which we can write it off, I mean, somehow write off the tsunami somehow, So even just postponing the collapse is in itself, I think, a good thing.
Oh,
And
sure.
since we know that the end result, I mean, this is probably also like a Jim Hansen quote that, the Stone Age didn't end because we ran out of stones. It was because we found out something good to do. And hopefully the fossil age doesn't run out until the Russians won't sell more fossils, right? So and I think we could really prosper by fixing that market deficiency there is in that there is no incitement in not changing, right? I mean, the engines, they are now going to have electricity, and they should. And of course, they are fully entitled to do that. But when it is as cheap to put on a wind turbine as it is to put up a coal plant, then of course it changed from one day to the next. Because
well, that's a tipping point. It's a different kind of tipping point, but I agree with you on that. And I think we're going to see all of electricity production go there quickly. Still, a lot of inertia.
That's only part
of
of
it. Inertia in our economic system and whatever. But back to your paper, and we were discussing some of the criticism, and I asked which did you think was valid? But you've read all through that, you've absorbed that. Based on all of that feedback that you've gotten on your paper, is there anything, if you were starting that paper today, do you think the result would be any different based on that feedback? Having read through the feedback and knowing how you did it, would you stand by what it says?
Yeah, I stand by what it says. There's more underpinning to be done, and of course, you can always, in hindcast and say, okay, this could go into that paper. That would be another paper. That's actually what I thought was that, okay, this is just like, another paper in the pile of getting there, right? And of course, this came out with a rather dramatic conclusion. So of course, we're also in some sense committed on that to really pin it down more.
So can you tell us, are you working on another paper now, and you have any time frame for that?
Yeah, and I mean the time frame is a few months, I would say. I mean, so we're doing it, of course, as as an academic. I'm also hit by teaching and other obligations and so on. So it takes the time it takes.
Great. Well, no, that's actually, from what I understand, some of Hansen's papers took years, and and then at the very least they take many months. So that's a pretty good record to do it in months from now.
Yeah, well, we're on it. I mean, the paper's been out for 6 months, so
right. Yes. And it did make this big hit for a few days, especially saying it could tip over in 2025. Whatever, the people played that up and talked about the Gulf Stream instead of the AMOC. Things, you had some issues like that in the press. But I'm a little surprised that something so important kind of dropped off the map and it's not talked about much at all in climate, even in climate circles, very much. I mean, it's certainly there, and it's, when you see a list of tipping points, it's listed as a tipping point. But that's not just you, that's also Hansen. By the way, if Hansen's paper comes out soon, which we're all waiting for, that will enhance yours, and together it's I think a very powerful set of research that warns us that we really should get our act together. And I agree with you that AMOC to me is maybe that thing that can get people to pay attention more than they have been, because it is so specific and whatever. So any further thoughts on what an AMOC shutdown world looks like? Have you looked into the impacts
we covered
yourself?
it pretty well here. So
okay. I want to thank you so much for your time, and sorry we had a little technical glitch.
If there are a few more minutes, I have a few questions.
Okay, go ahead, Eli.
So going back to what Dan just alluded to, what the AMOC shutdown world looks like. You mentioned that about 3 decades would be the time to start shutting down, on average, or the best guess. What I'm wondering is, and we have a fair idea of what things look like once it has shut down. In terms of what the average person living their life might experience, though, along the way before we get to the complete shutdown, but perhaps in the form of extreme weather events, whether it's floods or heat waves or cold snaps or polar vortices or what have you. Do you have any comment on what experientially it might be like in terms of things that people might be concerned about?
Well, I think we're seeing it already, but the thing is that we're looking at two things here. We're looking at global warming, and that's here now. And then we're looking at something locally in Europe that goes the other way, which would be a cooling. And they work in different ways. And if you look now, if we also talked about what climate models that simulate the shutdown would tell in terms of, so let's say in the American plains would be drier, and we would have more precipitation there, and more storminess, of course, over a cold ocean because of larger gradients. These things, but they're very uncertain in the models. I mean, I can do the hand waving saying, okay, due to that factor that we have stronger baroclinicity because the transport of heat to the poles is not as large, and that I can see in ice age climate data as well. All these things I can do, but down on the details, it's much harder. Of course, I can say global. Well, what we see here in Denmark is more showers, more rain from the sky. But we can just go to southern Germany and say, okay, that's the climate we're getting here. So that, in some sense, is a linear change of things, right? Which is expected. But all those secondary things on the way are very uncertain, I would say. And I would need to trust the climate models much more in order to rely on those for this kind of things. And
So I suspect your answer will be similar to my next question, but it's an important one. There are other things that can happen due to changes in ocean currents, or might happen. And I wonder if you have any observations or thoughts on these. One thing that's also been observed is increased heat transport into the Arctic basin by the Norwegian current. And I started looking into that because I was asking myself the question, well, what happens when sinking shuts down? The conveyor belt doesn't instantaneously stop because it contains a lot of momentum. Where does the current go after that? And it would seem that the two would fit, at least naively, that you would get more heat transport to the Arctic basin. Of course, if that is the reason it is happening, because we know it is happening, then there might be reason to be concerned that as the whole system shuts down, we get an excursion that is not the one that we're expecting with AMOC shutdown, that is less heat transport into the Arctic, but we'll get a transient of more heat transport into the Arctic, which can further melt sea ice and further warm up the whole system, including permafrost, and in particular melt the sea ice that has methane deposits above the gas hydrate stability zone.
Yeah. I mean, yeah. I mean, your guess is as good as mine, and of course I can only say, like everybody else, that it does make sense that people do climate models and do scenarios of the future to make these estimates. And I'll be very happy when the next generation of CMIP models come along, and especially if the models agree. But the problem is that kind of I think very good hypothesis that needs to be tested are not necessarily in the protocols for the CMIP calculations, which are basically you do this set of now it's SSPs, which means the amount of greenhouse gas concentrations. And that means everybody wants in the same direction scientifically, right? Because you want these models to be compared at the end. And maybe something is happening out here without us discovering that. So yeah.
So let me end with one last question on the AMOC and your paper. So let's assume that the AMOC begins to shut down, whatever that exactly means. Let's say 2025, and it's going to take 30 years for it to be completely shut down. Will we know that we've hit this point where it's shutting down? Will we see measurements that tell us, oh, look, it's begun the process of this 30-something year shutdown? Or is it something we'll only see in the rear view mirror?
Well, no, I think we will. Of course, we get more data, but we get only 1 year of data every year. So that, and actually when we started this, we had until was it 2020 or something like that, and during the work 2021 came along. We could put on one more point to the data released by NASA, I think it is, and it fitted all right. So of course we will have to monitor that going on, and of course the closer we get, or the further we are above the tipping point, the better we'll know. Okay. Because the data will follow, the statistics of the data will follow.
So you think that the way the oscillations will see something happening in them, and we'll be able to say, oh wait, that looks like we've crossed that tipping point. But and there, just the little hopeful sign you said, even if we do, because of that 30-year process, maybe it's not irreversible. Is it once we get 30 years in and it's shut down, you know, we didn't do anything, it tipped, we waited 30 years. My understanding is that's irreversible. You can't start it up again, except, you know, future changes in climate and things hundreds of years later. Is that, do you agree with that?
Well, that's what the theory tells, and that's what the model tells. If you run back, you get this classical hysteresis loop that you have to go really far back before you get up again. So that is, you know, that's what all, you know, the IPCC models and everybody would tell. This is the scenario. So we shouldn't get there.
Well, Peter, thank you so much for your, so we ended on some optimism, a little pessimism, but thank you so much for your time today. It was really eye-opening for me and for everyone else. Sorry for the technical problems. We'll get that fixed and post the video later today, so everyone on YouTube can see it. And we'll have comments, notes in the comments, links to your paper and things. I also want to remind everyone listening on YouTube to please subscribe to the channel and like the video so more people will see it. And with that, Peter, thank you so much. Very informative and very important discussion today. So thank you again, and we'll see you next time. Thanks, Stacy.
Bye.
Right. Bye-bye.
Bye. Thank you.
Thanks, everyone.